So thank you, Pek Har, for your time. And would you mind giving like a rough run through of like what do you do and what are your expertise?
Yeah. Okay. I've been a structural engineer for many years. In 2004, I started the Web Structures office in Kuala Lumpur with the founder, who was actually Dr. Hussein, who was based in Singapore and had operated in Singapore for 8 years before I met him. Long story short, we built a lot of buildings around the Petronas Twin Towers, a lot of high rises, such as the Grand Hyatt Hotel in KLCC. The newer one would be the EQ. We demolished the old Hotel Equatorial and built a new 50-story.
That includes the stairs above?
Everything. When we say we did everything, we did foundation.
I was just there a few days ago. I was like amazed by that.
Yeah,
stairs.
and I think there are two particularly interesting staircases there, very Instagrammable, which is the spiral one you see on the ground floor.
Yes.
And there's another one at the Sky Bar on level 51, which is actually a huge cantilever out. And also we did the Grand Hyatt Hotel. Okay, it's just a coincidence, but it also has a very interesting staircase just outside the ballroom. Then of course we did like Park 7. There are many projects. We Park 7 for STB, and we did Sunrise, the Summer Suite. Basically a lot of high rises in a lot of KL, like more than 12 very tall buildings. So, but it doesn't mean we're just doing high rises. We did a particular, it's actually a factory. It's called the Paramit Factory, P-A-R-A-M-I-T. It's a factory for a Californian manufacturer of medical devices.
Okay.
Named Mr. Bilu, from America. And what's interesting is that we did that together with the architect called John Bocock. He won it in a design competition. It's not a big job in the sense that it's about 40 million, something like that, but it actually went viral on its own because it doesn't look like a factory, it looks like a resort. So there's this huge cantilever out there, cantilevers about 12 meters, and the entire thing is not, we didn't need a steel truss, we just built it out of reinforced concrete without beams, just a flat slab, which is 250 thick.
Wow.
Yeah, so we do interesting things like that, things which are structurally challenging. But long story short, that was with Web Structures.
Yep.
In the year 2020, when COVID started, Dr. Hussein sold Web Structures to a very big Denmark group called Rambol, R-A-M-B-O-L, from Denmark. It was then, well, they have their own type of business, but I'm a lot more used to, or should I say, my interest is really to do very bespoke kind of structures.
Right.
Yeah, so last year I left Rambol, last September, and I've since set up my own design consultancy in structures called From Web. So that's where I am. Yeah. So, okay. So
From Web.
F-R-O-M-W-E-B, one word with a capital F. And the key thing about this word is not the word web, but really the word from. Because I've always been very interested in the point where you start. You see, I don't like to know, I don't think we should know the destination. I think we should just know that we start at this place and seek exploration, laterally, all kinds of direction, with all kinds of ideas. And then it becomes a journey just of exploration. And you know how it is, right? You don't intentionally seek something, but when you try to understand something, like we try to understand the entire performance of a structure, and we do a lot of analysis using the top grade software, hardware to do it. Yeah, we're kind of like very brainy, nerdy people. Yeah, and then suddenly you realize something. Suddenly you understand something, and something that you were not seeking for becomes the thing. It's something like the poem by T.S. Eliot, Little Gidding, where, after a long journey, you come back to where you started and know the place for the first time. So in a way, that captures our kind of design philosophy or design process. Yeah, so that's why the key word is the word from. I just know where we start. And I think it's very important to not have a fixed idea of where you end. Okay, that's where the name comes
I
from.
love that, because people have always been talking about destination and journey, but never really the starting point, right?
I mean,
that is
if you
almost
take it
what
in a
everyone
more
say.
like wider way, right?
Yeah,
I mean,
yeah.
to me, there's no point in knowing the destination, because in all of life, the end destination is the end of life.
Yeah.
It's only the journey that changes, not the end point.
Thank you so much. So let's talk a little bit about, I mean, when the news broke about the building collapsing in Thailand, and it was all affected by the earthquake in Myanmar, what's your first take on it? And because why we're having this conversation is because how much people have concerns over this matter, especially if it affects their buildings in Malaysia.
Yeah. Actually, factually, the first time that the word seismic forces or earthquake and how it affects buildings, right? It did not sort of like, hit me in the face this year when Bangkok experienced the earthquake and that one particular building fell down. We'll leave that aside, because that one particular building seems to have something wrong with it. I don't know anything about it because we're not investigating it or we are not privy to the information about it. But bear in mind that there's only one building that collapsed like that. The rest of the buildings stood up. I mean, they had damages to all kinds. That's what I hear in the news. The first time Malaysia, this part of our country, thought at all about earthquake, because before that we thought nothing about earthquake, was actually Boxing Day of 2004. December the 26th, the tsunami.
Right.
Yeah. So it was for the first time, KLC, Petronas Twin Towers and the tall buildings were all evacuated. People were in the building, but they felt the tremors. They saw things swinging, like the light swinging or whatever. And they were asked to run down the stairs and evacuate. Now, that earthquake, the earthquakes that hit Malaysia, right? All earthquakes are based on the tectonic plates. You see, like the crust of the earth is all like separate pieces of fractures, right? Segments. And these are called tectonic plates. And along the fracture line, they move. Some of the movement is sideways like this, like putting your left leg forward and right, side slips, or they are subduction, which is up and down like that. Or they can be a combination of the both. The one that hit us in December 26 and caused a tsunami in Penang and all that was it actually occurred off the west coast of Sumatra in a place called the Sunda Trench. Yeah, so it's really far away. It's more than 1,000 kilometers away, but we felt it. Well, that was a big one, right? Whereas the one that hit Bangkok actually originated, as everyone knows, in Myanmar. And Bangkok is also about 1,000 kilometers away from Myanmar, where it started, where the epicenter is. But they felt it because of a few reasons which I can tell you, okay? All right, then we're talking about earthquake. So let's quickly put in chronological order where we are regarding seismic design or earthquake-resistant building. So right after 26 December 2004, the engineering fraternity put together a team comprising academics and the Institute of Engineers Malaysia, and they were supposed to deliberate and come up with a seismic code. Right? So they went through many years of it, this way, that way, and all that. The key thing is to assign what they call a peak ground acceleration for each part of Malaysia. Okay, let me explain that. A lot of people think about earthquake and they say, oh, this is magnitude 8 on the Richter scale, and so is big. Actually, that the size, the number in the Richter scale has no relationship with the strength of the tremors or the shaking that you feel. Okay, the magnitude of the Richter scale is based where the earthquake begins, where it starts. So, for example, in the case, it started in Myanmar. I can't remember the place in Myanmar, about 10 kilometers below the surface of the earth. Let's say the town in Myanmar is called X. So the earthquake started 10 kilometers inside the surface, or at the epicenter. That's called the epicenter. So the Richter scale is measured there. Now, so when the earthquake starts, two kinds of waves radiate out. Sorry, it's a bit technical. So these waves come to the surface, and from the surface they spread out, propagate out as what they call surface waves. And it's these surface waves that travel over the surface of the earth that find their way to Bangkok, and like for us, from the Sunda Trench through Sumatra, passing by Sumatra and to West Coast Peninsula, Malaysia. So what we feel in Kuala Lumpur is a certain shaking force, let's call it, in simple language, right? Shaking force. And that shaking force, exactly let's say in Kuala Lumpur, is measured by a term called the acceleration of the ground. How much the ground accelerates, like a car accelerates, yeah? And that is called peak ground acceleration. So when we talk about zoning various locations, let's say in Malaysia, for different magnitudes of earthquake, we zone them according to this one number called peak ground acceleration. For example, in Kuala Lumpur, it's in the Klang Valley, it's already been zoned to experience a peak ground acceleration of 7% acceleration of gravity. Acceleration of gravity, like in high school physics, is 9.81 meters per second squared, and we have 7%
of that.
And it means the ground will shake like that.
Okay.
So that's what. Okay, so fast forward. So after this assemblage of people, technical people were set up in December 2004. Fast forward, their recommendations was presented to the federal government and say, Mr. Federal Government, please gazette this. And the federal government actually gazetted it on the 31st of December 2021. So that journey took kind of like how many years? 17 years, yeah. But it's gazetted into law. Of course, I think it's understandable. It's not that they're slow or anything. It does take a long time for the entire process and people to agree in all these peak ground accelerations. So there's another interesting point. It's gazetted law. That means Malaysia does have an earthquake code. Okay, it's gazetted into law on the 31st of December 2021. That means approved by the federal government. Yeah, but the code itself was completed in the year, I think it's 2017. So the cabinet took this time, which I think is part of the process. Okay. Now, but then there is another thing. The laws that govern building laws in Malaysia, I think you are an architect and you've heard of it. It's called UBBL, Uniform Building Bylaws. But the interesting thing is that this is governed by individual state governments. It's under the purview of the state, not the federal government, like Selangor, Kelantan, whatever, and the federal territory. Federal territory is like a state. Yeah. So for this to be absolutely enshrined in the UBBL of a particular state, the state government has to say, this is it, this is the law. So if you read the UBBL of a few states here and there, and I've read that, it's not that clear. It doesn't tell you have to design for wind load, you have to design for gravity loads. It doesn't actually say you have to design for seismic loads. It just generally says you have to design for all you have to comply with all the relevant codes and the loads that prevail at that point in time, right? So we don't have to get the exact state government saying, like the state of Selangor saying that in PJ you have to design for this or whatever. But I think engineers as of that 31st December 21 should design for this seismic load. So for the Klang Valley, it's 7% acceleration of gravity. Now, there were some tremors that originated from Bukit Tinggi, but they've taken all that into account. In coming out with these values of peak ground acceleration, they consider the last 50 years of tremors or earthquake. Another earthquake that we all hear about is actually in Sabah, Mount Kinabalu. It actually originated in Ranau, which is the town of Ranau in Sabah, near Mount Kinabalu. And Kota Kinabalu, the city of Kota Kinabalu is very near Ranau, actually, right? It's quite near. But interestingly, the peak ground acceleration for Kota Kinabalu, as gazetted in the code, is 4% G, less than the one in KL, right? And you might ask why? This is very interesting. It depends on the geology, the subsurface condition. What happens is that between, all the way from Mount Kinabalu to the beach of Kota Kinabalu, it's actually layers of sandstone. Sandstone-like rock, you know, like, I mean, you do some construction, architectural works in interior design, and I'm sure you're familiar with sandstone finishes. Yeah, the material from which the cladding comes from, in which it's a soft rock, but still rock. Okay, and it has very little what you call alluvial soil. That means sedimentary soils like clays and all that above it. That's why it's only gazetted as the buildings there are to be designed for 4% axial gravity. But Kuala Lumpur has a lot of alluvial soil, like clay, mixtures of clays and silts, and in Klang, well known for some marine clay. Kuala Lumpur, a mix of silts and clays, right? And that's why we have a higher value, because the surface wave that comes through alluvial soil is much stronger. It doesn't have so much ability to come through the sandstone. The sandstone dampens it.
Right.
Back to your original question. Why did Bangkok suffer so much when that earthquake that originated in Myanmar is so far away? Bangkok is along the Chao Phraya River. The river, usually by the sides of the river, is all alluvial. Bangkok has got Bangkok clay. The word is quite common. It's a soft soil condition. Bangkok generally has soft soil because it's on the banks of the Chao Phraya River. And if you follow the earthquake at the northern, if let's say we sail or we take a boat from the Chao Phraya, we go north. So what do you hit? The Mekong, right? And where does the Mekong go? All the way up Southeast Asia, all along the alluvial plains of the riverbed. So the earthquake started far away in Myanmar, but the surface wave can travel along this soft, not so great soils, alluvial soil condition.
How do you spell alluvial?
Alluvial, A-L-L-U-V-I-A-L. Yeah, V-I-A-L.
Alluvial soil.
Yeah.
Okay.
So I hope, I don't think we're going, I haven't gone into a huge reading or, but that's the first thing that struck my mind. What I'm sharing with you is, I haven't done any reading on it actually, but it's just what's off the top of my mind when I first heard about the earthquake in Bangkok. Yeah, so it's very dependent on the soil conditions. Yeah. And that explains why Kota Kinabalu is gazetted as a 4% G zone, and the Klang Valley is a 7% G zone. So but then we should design for those buildings. Okay, I think there are also different levels of designing for the building, right? Now, of course, the first and foremost, you don't want a catastrophe to happen, which means the structure has to design not to collapse. You don't want it to collapse and people get killed, right? Or very damaged or injured. And so the building stands up, and people don't get killed. It's not a fatal failure like you saw the building collapse and all that. Fine. But also there is now that's for strength requirement. But for serviceability requirement, a building can suffer a lot of expensive damage, needing very expensive repairs, even if the structure stands up. And then I think that's the situation Bangkok is in now, because all your glass cladding has fallen off, has cracked, and all that. Your pipes all have gone wonky, and you need to replace all that. That's the serviceability aspect of it. So in a fully seismic compliant building, it's not just the structural engineer who has to participate in this design process. Right. Okay, we are the first one. Okay, we make sure it doesn't drop down, and that's possible, right? How we do it is, we use a 3D modeling software, structural software. We apply the earthquake load based on the value of peak ground acceleration, and we actually shake the building, the computer model building, and so that every element of that building, be it the slab, be it the column, be it the wall, is subject to that earthquake force. Just like we subject the building to wind, to lateral forces. Seismic is also a lateral force. And then we will know then all the forces that act on each element and the frame, be it reinforced concrete or steel, and then you design accordingly, according to it. Then you would also inform your collaborators in the project, like the architect and the facade consultant about the movements we expect. So that, for example, the facade, they can design the gasket to account for a bigger movement or the gasket to have a bigger depth, or inform the architect that this building should not have very brittle walls like made of aerated lightweight block, and we have to look into all those things. So it's actually a collaboration. So the structural engineer makes sure that the building doesn't suffer a catastrophic collapse. But the other trades have to come in to make sure that the building owner doesn't suffer a huge financial loss to repair it during an earthquake. Where are we? And that's how we design it. That's how we are now designing our buildings everywhere in Malaysia in accordance to this code. And this code is called the National Annex Code. It's called MS for Malaysian Standards EN 1998 or something.
So it's always back to the PGA that we spoke
Yes,
about.
correct. Back
And
to the and the
based
method
on
of
the area.
and the method of analysis, or what's specified in the code, is actually following EC8, Euro Code number 8. Yeah.
All buildings has to follow.
Yes, it's just like all buildings have to follow the UBBL, which is designed for live flow. I think everybody has heard about that. You know, like if the usage is for a public assembly, like disco, or well, no one goes to disco anymore. You know, like a F&B area, it's a higher load than a resi floor or whatever. Yeah. So
Those are the things that most of us can see: the width of the corridor, the width of the exit, you know, the ventilation. But no one actually sees structural calculation. So
yes,
right,
I think,
and that's the hidden part that people always like no one talks about.
Yeah, no one talks about. In a way, it shows that engineering has been good in the sense that people assume a building stands up. Nobody goes to a building and thinks that, oh my God, it's going to fall on my head, right? So, but when these things happen, or you just, some people suffer like a landslide. Oh, there's another very interesting, to me, the most interesting project I ever did in my entire life, which happened, you know, there was this huge flood in the Klang Valley. You might remember it. It was on the...
Sri Muda?
Correct. 18 December 2021. Right? There was this 3 days or whatever of continuous rain, and all the rain that was supposed to fall in 1 year fell in 3 days or whatever it was. And Sri Muda, people were in boats and all that. Well, in the same event, the same huge storm event or huge rain event, there was a condominium in Bukit Tungku called Seri Duta 1.
Yeah. My project was there. It was held.
What do you mean your project was there?
I was a small little interior project that was doing a house, and it was held up.
Where? Oh, because of the
Sri Muda 1 or something, like, yeah.
Okay.
So everyone evacuated. Lovely.
So it was called Sri Duta 1, right?
Yeah.
And I know nothing about that except what I read in the news. I mean, they were quite like dramatic photos. You saw the piles cut off and all that, right?
Yep.
You know. Well, it happened on the 18th of December, sometime about almost 10 p.m. in the night. Then they all evacuated. 10 days later, I got involved in the project. No, I was not the original engineer on the job. It was built in the 1990s, so it's very long ago. But the MC, the management committee, the owners, somehow got my number and phoned me. And long story short, it was really bad because before this, they had spoken to like almost 20 engineers. They told me that later because 10 days had passed by. Every day, two doctor of something, PhD engineers would visit them, or they called them to visit, and they would have various ideas. But their key question was this. Their key question was, okay, we are lay people, all right? We are fine with you doing whatever you think you need to do. Can you want to rescue the building? But can you certify, at the end of it, will you certify that the building is safe for occupancy? Because, you know, they've just lost the value of their home, right? And everyone said no. So when they asked me the question, I said, I don't understand this question, because obviously if I were to, any engineer were to be involved to design the building or to design the remedial for the building or save the building, then you must believe in it enough to sign off, right? Yeah. So anyway, long story short, I got a job And when I got on the job, to be honest, at that time we were already taken over by Rambo, and I don't know whether you want to put this in your record or whatever. We can decide that later. Okay. I didn't tell them anything. I kept it a secret from the management of this big corporate because I knew they wouldn't take on the job. It's too risky because the building is tilting every day. It was going to fall.
Wow.
It's not that it just like that and then became like this. It was falling. You just don't know when you're going to fall.
It was slowly leaning by the centimeters
Every day the degrees the inclination is increasing.
Crazy.
Yeah.
Wow.
It was moving.
Wow.
So we got into the job and actually I have a lot of footage and I have a lot of records of the whole thing, from photos to we had a very small video that we made ourselves at the end. We saved it. In 4.5 months later, sometime in April of 2022, I declared it safe. We stopped the tilt. And if you go back now, wow, it's even more beautiful than what it was. So, that was a super interesting project, but very challenging because the interesting thing is they didn't have drawings. There were no structural drawings, and we weren't the engineers, so so I think that was the most challenging thing ever. We can talk about that another day, but when I talk, but you see, the people who experienced that landslide, the owners who were there, they don't take structures for granted, I can tell you that. So just like if you experience the earthquake, even if everything cracked, you start to think again, It's just like we drive a car, we don't think of an accident before we had an accident.
Absolutely.
Yeah, so I think it's the same things for structure, and I think that, I think every engineer should design it in accordance to the code. It's quite, you need to comply anyway, yeah.
Is there a certain amount of margin of
yes, there is. There's a
calculation
cost.
that you double or triple?
No.
It's not about the load?
No. The code already specifies all that. You stay with, let's say you're in KL, there's 7% accessibility. Using that as your base force, they have all those methods to, they have factors of safety within that. But you see, factors of safety are not up to the whims of the engineer. Let's make it very clear to you. We can't, because the building law, the UBBL and the codes, you just have to follow that. Yeah, I think there is this kind of, I think a lot of people think that all engineers over-design. Yeah. Well, unfortunately, I don't want to say anything negative, but the engineering fraternity has to improve the way they do things here, in particular, in which why do engineers over-design, right? It's only based on why do we put more money in the savings or something like that. Right? It's
assurance.
because you're unsure. No, it's not assurance. The word is you're not sure of the performance.
Right.
Right? Just like F Formula 1 driver has no issue driving a car at 300 km an hour because he knows
It is.
how it will feel, how it performs, and he's confident. Same with engineers. Over-design is only caused by people with a lack of sureness that they understand the performance. And by the way, let me tell you, over-design doesn't make a building safer. You see, this table has 4 legs, right? For a structure to fail, you don't need 4 legs to fail. You just need 1 leg, and not all legs carry the same weight. So if you simply increase the size of all the 4 legs, but there's 1 leg, you didn't understand its behavior properly. If it fails, the whole building fails.
Okay.
So throwing money at the problem or throwing material at the problem does not help. At the end of the day, it's again back to the design process or philosophy that I was trying to tell you about. You need to be very deep into the concept, understand the whole performance in depth. And that's when good design happens. In all products, like even in Apple, right? They spend a huge amount of time thinking about things that most people don't think of. They just want a phone that works, but they want to think about the tactile feeling, the user interface, and things like that. Yeah. So we also happen to do the Apple store in TRX.
Would you mind sharing a little bit about that? Because I I was sharing you, I took a video of it, I talked about the interior, the design and all, looking at the
I think I saw that video.
stairs.
Yeah, because you took some good videos, because at that time I hadn't taken any photos of it.
So
Yeah.
I think people will be very intrigued to understand how it actually works. Like maybe the things that you can only share. That you
Yeah, I
feel
think
that
I have
it's
to
nice.
check what are the things that I can share, what are the things that I cannot share. But the one thing I can share today,
Yeah.
really, we can have separate talk about another day if you wish, is that my team and I, and they are here now today,
Yeah.
some of them are here, totally enjoyed that assignment. Somehow we're very attuned with the way the client
Foster.
thinks. Foster, the architect, and also the client Apple. Yeah, just for you to know, when you come into the store, it's level 1. I think you know that, you took all those videos, right? It's the entrance, right, where all the goods are there. Then you go up the stairs, that takes you from level 1 to level 2. That staircase is a normal dog leg, in the sense that you go up, there's a mid-landing, but the mid-landing is not connected
At all.
at all. Then you go up to level 2. That's fine, it's like normal. Many staircases are like that, even in 1960s or 1930s. But the next one is difficult, because from level 2 to level 3, level 3 is the garden. The TRX garden, the roof with the dome is, because they're very high. So from level 2, you go to the first mid-landing, the lower mid-landing. And then you have to take another flight to another mid-landing on this side, the upper mid-landing. And then you go another flight. So you have 2 mid-landings which totally cantilever. But that's not the most difficult thing. The so-called support at the top, where level 3 is, where you walk out to the garden, right? It's not actually on a very rigid floor. It's sitting on another cantilever, because that whole atrium void is cantilevering out a distance of about 6 to 8 meters. So you have like a diving board situation there, and you want to put this staircase on it, and this staircase is also like cantilevering here and cantilevering there. Static, in terms of structural statics, like you can make it work. But the problem is structural dynamics, because you see, I mean, you know all this, right? Like generally staircases must be designed to have a natural frequency of 4 Hertz to 5 Hertz, right? But this staircase can never achieve that. Not the way it is sited and the way it sits on the diving board. It clocks in at 2.8 Hertz, far below that.
Okay.
So the whole challenge became structural dynamics. And that's what we did.
Wow.
But the staircase is, we're very happy with it, because it also, after it was completed, because it's what we call performance-based staircase. That means it's not following those rules of thumb or guidelines of the code. It's very code compliant, but the code requires this to be its actual performance, its accelerations again, and its behavior to be measured as built in real life. So we got this university, USM university, they came with the measuring devices, and they measured its damping ratio, they measured its acceleration, and all that. So we had to go through all that and check for fatigue checks. Wow. So this is actually a kind of work which a lot of structural engineers don't do. Right, but we developed that knowledge within our team during the project. So I'm very proud of it.
Wow, I think a lot of people should know about it. Like, instead of just walking in and admiring how beautiful it is.
I'll just give you a clue.
Yeah.
Okay, you can't feel it when you walk. Okay, you go from level 2 to level 3, but you can't feel it if you're just going up the stairs. You can't. What you do is you stay still. You stand on either of the 2 cantilevered mid-landings. One near the lift core, the other side. Just stand there, don't move, just stand. And wait for someone to walk up or down the stairs from level that you will feel it. It's a very low, like this.
It's not
No.
It's just
No, you probably have felt like kind of so-called bouncy staircases. Like if you do a lot of interior job, a lot of interior staircases. Like I did also the small staircase, but it was a lot of Instagram in Troika. Troika skydiving, Cantaloupe last time, and Fuego.
Fugo.
That little stairs, they want to throw it away now, but that one that has strings hanging from it, used to go up to the Italian restaurant. That stairs I did. Yeah. So it's a different feeling. That stairs also has a different frequency. You don't feel so stiff. But that is more like a like that, like a bit bouncy. You feel like on steel. This is different. It's a low rumbling. On this, the store stairs, the TRX store, when it's low. So you actually feel like you're on a ship. You got to stand there and
it doesn't always happen to most stairs and structures within interior, because mostly it's just
correct.
immediate hit.
Yeah.
That's
Even
impact
you
you
say
can feel.
even you talk about that so-called staircase, as far as in EQ, it's not like that. It's not like that. Because that frequency is it's short of 4. It's like, but it's 3.6. This is really low, and bear in mind the human natural frequency of walking is about 2.2 hertz. So this thing we learned in high school called resonance. So when the natural frequency is equal to the usual walking frequencies, you can enter resonance, and then the staircase.
It's dangerous.
Correct. So we went through all the scenarios, like ranging from 3 people marching to people. It's a lot.
So you're looking at 2.2 as opposed and very closely to 2.6 or 2.8 that you said.
That's why we had to study this staircase for 2 years. You see, we can design a high-rise building in 3 weeks. I kid you not. But it took us 2 years. So it's not the size.
Oh, that's something people take for granted.
Yeah, I can share something. Okay, yeah, you better go. I think something on.
Maybe I love this topic.
You like this topic?
I love this topic so much because it's something that we don't come by all the time.
You don't come by all the time.
After the phone call with you, I told my wife, I had this crazy conversation with this engineer. It's like it blew my mind. I don't even know where to begin. So yeah.
Yeah. So.
And the roof, the dome, you guys did that calculation? Was it?
No. You see, the dome we were just doing the base checking of it, because the team that worked on it, is the glass. It's the glass specialist doing it. The team doing the dome in particular was EOC. It's Pek Har from London. They are specialist glass and facade engineer. They're structural engineers also, very good ones from London, who actually were Apple uses the same people. They also did it's on their website. Apple also used the same guy who did the Cupertino. Cupertino, the Steve Jobs theater, the one that the roof is sitting on the structural glass that is frameless. Yeah.
Wow. So they did that and also did the one in TRX.
They did that. So our job for that was only the base reactions and something to do with that.
And again, the base that you were talking about is actually cantilevered.
Yes, right? We did that. We designed that. We
so the entire walkway that's right under the dome is actually fully cantilevered.
Fully cantilevered.
And it's hanging off another building structure.
Yeah, and then the pool stairs has to sit on that.
And all of this had to be designed way before TRX was approved for, because you had to create this.
The mall is. There's one more thing that we did. No, there's a mall, right? It's like it's not a standalone store. It's within a mall. But you may notice that if you're in the store, the clear span across has no column. It's actually 26 meters across. We removed the middle columns.
So what you're saying is the mall was designed to have a column there, but you guys removed it.
Yes, we took it out, yeah.
So it's not that it was designed to fit Apple there with this design in mind?
No. That part of the mall, was that particular that removed the column thing wasn't built yet, wasn't cast yet. Yeah, we're waiting for the design. And there's one more thing we designed, which this is seriously no one notices. They even notice it less than the staircase, okay? In TRX, there are a lot of pedestrian bridges across the atrium. Yeah, you cross over the atrium and all that. If you look at it from the side elevation, it's a white color cladding paneling, right? And it has, the depth is about 950, the thickness of it, the depth basically. And there was this pedestrian crossing right in front of the store. I think you can see it, right? And
Coming
it was 950.
Left and
right. But Foster didn't want it to be 950. It's too thick because it will block the Apple logo.
Yep.
They wanted it half of that, 450. So we took on that job. So that particular bridge we designed. We reduced it to half its depth.
Because the logo was just right at
the it will block. The line of sight will block. Wow. So these are some of the interior
Love it, love it. Wow.
I don't know whether I've said anything wrong, so I have to check the NDA and curate
I'm
it.
so
but-
excited to like edit this video. So maybe the last question, if I can share with you, over the phone you shared with me something really interesting that caught my attention was every part of Malaysia, because you talk about the PGA, right? Everything is not designed the same way. And you mentioned something very interesting. If you were to be on a 20-story building, you might just be safer to be on a 100-story building.
Yes. No, what I meant by that was, you see, you have to design for wind. Wind is a lateral force. So the taller a building is, the much higher the wind force gets a lot in a parabolic fashion. So when we talk about very tall buildings like 80 stories and above, I mean we have so many in KL, right? We have Mulia Tower, we have Petronas Tower, we have the Mulia is now called the Exchange 103, and we have PNB 118 and more coming up. There's a lot of wind force, the wind pressure acting on the building and swaying it. So actually the 7% G that we are zoned in for seismic is a very low zone. It's one of the lowest in the world. In fact, very, very low, right? So the seismic force is not that great. So, but the wind force is very likely to become the critical load condition rather than the seismic for tall buildings. So I would feel, okay, let's say I don't know whether a building is designed for earthquake just because it's kind of new in this part of the world. Let's say I simply think like that. But I do know that from the very beginning, all buildings should be designed for wind. And when you have a very tall building like 118 or whatever, right? The good thing about all these very tall buildings, a lot of people feel unsafe. I talked to my mother, and she said, "Oh, I can't live in this tall building because it's so scary." On the contrary, you see, anything, you can have made an accident whether you are in a Kanchu car or you are in Volvo or Bentley, right? Then you buy a car and you convince yourself, oh, I'll buy a Volvo because it's has more safety measures. That's true. It's not that it's untrue, but people still die in a Volvo, right?
Yep.
Because what governs it more is how you drive.
Yeah.
Correct?
Yeah.
Your performance. It's the same with building. You see, unfortunately, not very often people think, a lot of people think, just building a very short building. It's only like 5 stories. So many 5 stories, 10 stories. So what do? They want, you're an architect. They want to have the cheapest engineer, the cheapest architect, the cheapest everything. Sorry, I'm not saying this to insult people.
To reduce
They think anyone can do
overall-
it, let's put it. And they have their own thinking, which I think is faulty, that this saves all the money. Which is not true actually, because fees, design fees are very low compared to
Overseas.
the actual construction
okay.
fees. Yeah. But that's why those buildings very often don't have the rigor put into them. They lack rigor in design. Like a lot of our jobs, we're not the first engineer on the job. It's only to get into trouble. Then, then we are on the job. So when you talk about tall buildings like that, no, they have a high degree of rigor. They would have got very good engineers who know what they're doing and all that, like Burj Khalifa, like Kingdom Tower, like Foster does a lot of these jobs. It's not that they don't do small jobs, but they do challenging jobs. So I would feel a lot safer because I think those buildings are properly designed. So, but back to the topic that the wind force is very often the critical force condition compared to seismic for very tall. So I would expect like a 20-story to suffer more in an earthquake rather than the wind force, because you see, I think what is dangerous is when in design, as a designer yourself, you are aware that if you have thought about something in the design, it's always can be handled, and that's what's really great about if you were to all the top architectural firms, right? It's because they have a design rigor. They thought about everything. Everything, doesn't mean like the architect just thinks, I want this shape, I want this form, I want this function, I want this space, right? and I want columns here. That's called not listening, because every building project is 100% a collaboration. So working with Fosters on quite a few jobs, I can honestly tell you that what they're great at is listening. They listen to mechanical engineer wanting all kinds of ducts, electrical wanting, I don't know, all kinds of substations, structure wanting something, and whoever. And they're able to take all these things that start as problems or obstacles, but somehow they have a way to make it into something better than what it was. And I think it's a good kind of way for a project to work. And to me anyway, I think that's why they're so successful.
Wow.
Like, we are engineers, but I always train them to pay attention throughout to everything, including interior design, including how people fix things, to things that should not bother a structure. But
Just like the 950 slab, that is also a problem that seems simple, but actually it affects.
Yeah, it affects because you block.
So,
yeah. So that's it. And I mean, I hope we work. I mean, we want to work with like-minded people, and I think we do.
I love. It's very refreshing of a take that you have, and in terms of going into how detailed these things, it's not just what people see on the surface level, being safe or unsafe. It's just way more than that.
Yeah.
There's so much calculation to it.
So correct, because of course I see people going to the store and they're all busy looking at which phone they want to buy, which cover they want to buy, the color of the cover, and all this kind of, but nobody like, staircase is just a place to go to, because we need to,
We just need to get up there.
we just need to get up there. Actually, we need to go to the garden, and
It's absolutely something people need to take into
yeah, we need to go to Kenny Hill's
Appreciate
Bakery, so that's the fastest way. Yeah.
Yeah.
Okay.
Appreciate it.